שלום לכל מי שצופה בנו עכשיו. אנחנו נחכה עוד כמה דקות עד שיתחיל רשמית הוובינר בשעה 3. נחכה לכל המצטרפים ונתחיל. שלום לכל מי שהצטרף אלינו. אנחנו נמתין עוד 2-3 דקות שכולם יעלו ואנחנו נתחיל. אני אציין שאנחנו גם משדרים לייב ביוטיוב. שלום לכולם, שלום לכל הנוכחים וברוכים הבאים לוובינר בנושא יישומי בקרת מנוע עבור יישומים רפואיים באמצעות כלי MATLAB וסימולינק. מדובר בוובינר הרביעי בעצם בסדרה שעשינו לחברות המדיקל בישראל. היה לנו על נושא של פיתוח והטמעה של מודלי AI, על לימוד מכונה ולמידה עמוקה, ועל תכנון מבוסס מודלים, MBD, ועכשיו אנחנו בעצם בהרצאה האחרונה, את ההרצאה הזו שתסתיים ואת כל השאר קודמותיה תוכלו לראות בערוץ היוטיוב שלנו, אנחנו מזמינים אתכם להצטרף לערוץ. את ההרצאה תעביר שאנג צ'ואן ואנחנו תכף נעבור אליה. אני מזמינה אתכם לשאול שאלות במהלך ההרצאה, יש צ'אט של Q&A למטה, שאתם יכולים לשאול את השאלות והמרצה תענה בסוף הוובינר. Now I'll switch to English to introduce Shang Chuan. So we're going to talk about designing a motor control for medical devices with Simulink. Good luck, Shang Chuan. And you're on mute.
Can everyone hear me?
Yes, perfect.
Okay, perfect. Thank you, Mo. So hello, everyone. Welcome to YouTube and Facebook. Welcome to this webinar on designing motor control for medical devices. My name is Shangchuan Li. I'm the application engineer at MathWorks. I'm based in Dallas, Texas. My specialty is in motor control and power electronics, and I mainly support customers from industrial drive and automation and energy utility. But I'm more than happy to support any customer who is focused on motor control. So just remember, I will present the webinar for about 45 minutes, and I will leave for question and Q&A afterwards. So here's today's agenda. First of all, I will show you a demo for a motor control system with Simulink. Then I will talk about why and how model-based design can help and accelerate your workflow. And next, I will dive into how to build a motor control system from scratch by using Simulink and Syncscape, including how do we parameterize the motors and design the control system by generating pulse width modulation waveform, PWM, for inverter drives. And as we know, most of the control algorithms eventually are digitally controlled by microprocessor or DSP. So we will also talk about how to quickly generate a code and deploy it to a target. And this can be really useful for process in a loop and real-time control application. So the key takeaway for today's presentation is with model-based design using Simulink, it will allow you to reduce the development time from design to implementation by 50% or more. And from there, you can parameterize your motors and design the control algorithm in only one single environment, which is Simulink. And after you finish all your control design, and then we can generate efficient code from your control algorithm and deploy it to any target processor. So the idea of the model-based design in Simulink is basically dominated by two parts of the words. First is the software side. So basically we got the closed loop PID controller that comes with input and output data. And we design our control logic and generate a code into the controller. And the flip side of the word is the physical hardware. It can be electric-mechanical system converting electrical energy to mechanical energy or thermal. So in Simulink, what we offer is we can modeling and control the multi-domain system in one single environment. And next, I will quickly show you a demo. How do we model the motor control system in Simulink? So as you can see, this is the interface for Simulink model. Now, what I'm trying to modeling is the physical plant model for the motors. So as I zoom in, you can see we got the three-phase inverter is being supplied by 400 volt DC bus voltage. And we also have PMSP, permanent magnet synchronized motors over here. And we also have a mechanical sensor to detect our speed feedback. And we also have a motor, load, and inertia to represent this motor with inertia. And we can also have a capability to have an ideal torque source to apply to this motor. So on this side, we have our controller. Now we have a 2000 RPM speed command. And we also have a PI controller to controlling our speed and current regulator. And one of my favorite things to do to see the dynamics response is just directly click this run button. So we can quickly see, okay, so looks like I have some Google ensure that actual model. Let me quickly see, okay, what's happening here. Let me just save this model. Let me quickly run again. Hold on a second. Let me close this one and reopen it.
Let me remind all the present that you're all welcome to ask questions during the webinar. Down you have the Q&A chat, and in the end, we will answer everything.
Yep. So now, yeah, I was having like some error issues because of the definition of my blocks. So now I'm able to run my simulation result by clicking this run button. And as the simulation is running, we are observing the signal for the speed feedback. So basically we are comparing the speed command and the speed feedback that we just measuring from the mechanical sensor. And we also have torque feedback that we're trying to observe, and also the three-phase current feedback. So we can double click this scope, and as you can see, the simulation is showing yellow one is our speed command. So we're ramping up our motors around 2000 RPM, and the blue one is our speed feedback. And this is a torque response, and here is the three-phase current. And we can also zoom in to see now our three-phase current signal. So as you can notice here, if we look closer to our speed, as you can see, there's some discrepancy between this speed command and speed feedback. Typically, in motor control, we generally will trying to go to our PI controller. The traditional way is we go to our PI controller to tune our proportional or integral gain. But one of the nice things about Simulink is you can leverage the Pid Tuner app to automatically tuning your PI controller. So now I'm just opening up the PID auto tuning app. So essentially what it does is, yeah, let me just quickly grab this GUI interface for the PID tuner. So as you can see, now we are showing you the blue line here is the tune response after the system will help us to identify the linear model from our plane model and design our own controller. And the blue dash line is the original block response. As you can see, it's very relatively slower than the tune response. And one of the nice things about PID tuner is you have a capability to adjust your response time if you want to faster response time or more robustness of your transient. So it depends on how do you want to adjust your system to meet your requirement for your speed controller. So now if we satisfied with our step response for our speed, then we can also see the parameters over here. So just quickly show you. Okay. Looks like, okay. So just want to show you the comparison between the blocks, the original PI parameters and the after the tune parameters over here. And as you can see, the settling time is a lot faster than original system. And although the overshoot is higher, but it's still acceptable. So once we satisfied with our tune parameters, we can click this button to update the parameters. So, and the parameter will be updated over here. And now we can compare our running our simulation again and see how is our system has been improved after we utilize this PID Auto Tuner app. So as you can see, the simulation is running over here. And one of the nice things we can also observe by using a diagnosis viewer to see how does the simulation is executing our code. So now I would like to double click on our result. So as you can see now, the speed response of the speed feedback and speed command almost matching with each other by utilizing automatically PID tuner. So let me switch back to the presentation. So I just show you the demo of motor control in Simulink. So basically the hardware motor is modeled by ThinkScape Electrical. So with the ThinkScape Electrical, we can also model different level fidelity for different purpose. What I mean here is think about if you are a system architecture engineer, you probably only focus on system level simulation. So you can use the one parameters to model a system level simulation of your electrical system, for instance. And if you are an electrical engineer who is focused on component level simulation, like spice level simulation, you can choose the detail level simulation, including some saturation effect to do more harmonics analyze. And the trade-off for long parameter linear model that can take less computation time, but fast simulation to allow you to run large system level simulation. As for modeling complex and detailed component level simulation, considering the non-linear effect, it will take longer time to, but at the same time, it can give you more correct, realistic simulation results. So now I would like to give you an example on how do we model different level of fidelity in inverters in this case. So as you can see from this video, we can choose the level of fidelity by either we want to model average model. In this case, we are modeling the switch device inverter, which means we want to modeling our inverters more detail. So this is the different choice of different level of fidelity for our inverter. So in this case, we trying to compare what's the difference between the average value inverter and switch device inverter. And if we look into the average model inverter, as you can see, it's an average voltage source converter, and we can defining our power loss. And it's a very simplified model, but for the switch level device inverter, we have a capability to output our gate signal to our power semiconductor. And in this case, we are modeling the switching devices, the IGBT, but we also have a capability to select different devices. And from there, we can specify our parameters. And now I would like to compare different level of fidelity. So now I run the simulation, and then later I can compare through the data inspector. Yeah. So now I basically run 2 times of simulation. So now it's we are trying to compare the signal. The first round is our switch level inverter, and the second round is we compare the 3-phase voltage. As you can see, we compare the 3-phase voltage and the 3-phase current. And the first round showing here is we using the average model inverter. In the first round is we are modeling the switch mode inverter. As you can see, the difference between this modeling for the switch level inverter, it will give you more like a PWM double hump PWM output. And as you can see also for the switch mode inverter, it will give you higher fidelity level, and including some switching effect of a nonlinear effect compared to the average model. So, okay, I already talked about modeling the motor control in Simulink. Now I want everyone to sit back and think about what's your current workflow or traditional workflow looks like whenever you start with a new project. So typically we have several requirements that we have to meet our design in the very beginning of our project. And then we will start working in the design phase. For instance, for me as an electrical engineer, I will start design my electric circuit on the SPICE simulation tool. And my colleagues who is a machine design engineer who is using other like FBA tools to design machine and firmware control engineer will start working on writing the code for controller design in C. So essentially everyone work on their own project with different tools. And until the final stage, which is implementation stage, they will come and meet together for integrate all the component into a control system and test it. And as you can see, there's always a barrier between those of each engineer, especially in the early design phase, but also in the implementation stage, which will slow down the entire development process. Like we couldn't manually coding is slow, and it's really difficult to compare the design between your design phase and implementation phase. And also you cannot find the problems using the hardware prototype. And also we couldn't validate our design against our requirement in the traditional design workflow. And so what makes model-based design difference is that first, we break the wall between you and your colleagues. Now everyone can work in the same environment in Simulink, so which means we can model the physical hardware and optimize our controller in the same platform in the early design stage. And then we can save time by automatically generate the embedded code from the model. And this is super useful for me as a motor engineer, for example. In the hardware testing stage, a lot of times we have to tune our controller parameters to make sure our hardware perform correctly based on the requirement. So all we do is change our code, but not changing our simulation. So by the end of the project, the modified C code and the simulation are not always consistent. So the challenges that we often heard from our customers is that before they use model-based design, it was hard for them to manage the project because the previous C code was designed a few years ago, and due to the inconsistency between the production code and the simulation model, they have to redo the test and verify the design all over again. So with a model-based design, we can always go back to the simulation model and change it and generate code. So we can always have a latest up-to-date code and the model. And on top of that, we can do hardware in the loop test to save the cost, especially in the implementation stage. And I will talk about that later slide. And from there, we can also detect the error right away with the continuous verification system. So the next question you might ask, what if I already have a complete design of my electric circuit model and I don't want to redo the modeling again? Or you might ask the question like, can I combine my existing CAD model to a Simulink? Can I import my finite element analyzed machine model to a Simulink? So the good news is yes. So we can co-simulation your original design in simulation environment and verify your design in the entire model-based design workflow. So now I would like to show you quickly how we build a motor control system from scratch in Simulink. So let me go back to the Simulink model again. So now, as you can see, we are in the MATLAB environment. One thing to notice is that in the MATLAB, we have a MATLAB tool strip over here, and we can select here. Over here, we will select the Simulink to start our Simulink page and then do the modeling. So now I would like to just click this. It will direct me to the Simulink start page. And from the Simulink start page, it can give you a choice of you can either start with the blank model or blank subsystem or library. And since we are trying to build an electrical system for motor control, so I would suggest to go to Thinkscape, and then under Thinkscape, there's a template for electrical part. Of course, if you are interested in different domain, remember the Simulink is a multi-domain system, so it will allow you to model in like thermal domain or mechanical or moist, gas, hydraulic. So any domain you can modeling, it's all included in Simulink. So in this case, I would like to model the motor, right? So it's the electrical domain. So I will just create this model from here. And then it will bring me to a white canvas of the Simulink. So it will give me a template over here. So far, I don't need this one, so I just quickly delete this. So now we are trying to build an electric motor, right? So the first things we can find is we can go to our library browser. And as you can see, the library browser is including a lot of different toolbox. Like the basic one is Simulink. Inside of Simulink, we have like math operation to allow you to choose whether you want to do the adding function or divide function, or if you are interested in command like source command, we can output like pulse generator or sinusoidal wave, like over here. So as you can see, there are a lot of capability allow you to build your own control, and also different toolbox like aerospace in different domain. But for today's presentation, we only focus on Thinkscape, especially for electrical side. So we will go to Thinkscape and electrical. So I will quickly show you. So, okay. How do we founding? Okay, so this is a foundation library. So I will go to Thinkscape, and under here, there's a Thinkscape electrical. So to finding our electric motors, we will go to electric mechanical system. And then since we are interested in permanent magnet machine, so I will go permanent magnet machine, and then quickly grab this block. So we got the motors. What else we need? We definitely need a power supply. So the other way to quickly grab our component is by typing voltage source in this case. So we can quickly grab our voltage source here. And it's very intuitive. You just connect the wire over here. So now we have our DC bus voltage. Since the motor is being excited by the AC voltage, so we definitely need a converter to convert our DC power to AC. So we also can go to the semiconductor converters, and now we are interested in average value voltage source converter in 3-phase. So we can quickly grab and it's a quickly grab and drop environment. So we can Control I to flip our component, and then I will quickly just connect to the wire over here and to show you. So now we have our electrical side. So in order to represent our mechanical side of our motor shaft, we can also go to our library again, and this time we will go to foundational library, and we were interested in some mechanical components in this case. Like if we are interested in looking at the speed or motion, so we can grab the rotational motion sensor over here, and then we can also have a mechanical source like torque source. And we also need some moments of inertia to represent our motor. And we also need a mechanical rotational reference in this case. So now we have our components. So I will just quickly connect all this together. Okay, so yeah. So I can give an idea source. Okay, this one got to be connect with this one because this is represent the mechanical rotational reference to connect with the case. And this is represent the rotor shaft. Okay, so I also need some resistors to resistors. I will quickly just define our resistance value. And I can, by right click and then copy this electrical reference. So as you can see, we have our electrical side of the motors, and we also have our mechanical side. And as you can notice, like in Simulink words, we differentiate the different domain of physical system by colors. For electrical, we try to represent by blue, and the mechanical side we represent by green. So now the next step is we got to specify our parameters, right? So before this presentation, I already create this script for all the parameters for our machine. So I can quickly go here and then just defining our, for example, I want to define our DC bus voltage. So I can just type VDC, and which will represent 400 volts DC bus. And here I would like to define my motor parameters. And like we need to define our number of pole pairs. In this case, I already defined in the MATLAB script, so I can quickly just go here and type these parameters. And here I'm defining a Perner magnet flux linkage. So, and then I also need to define our stator inductance. And here we can also specify we want to be nearly Henry in this case. And then our stator resistance. Okay, and then I will hit apply. And then the other component that I need to specify is the moments of inertia for the mechanical part. So now I have all my parameter has been defined. One thing I need to do is definitely I need to run this machine, the MATLAB script, in order to load it all this parameter to the workspace of the MATLAB. So in that case, my simulation model will identify all this parameter has been entered to here. So I can quickly by click do Control D to see whether, okay, now the Simulink can reading all the parameters that I just defined. So now we already have our physical system. We also need our control signal, right? So one thing to can represent our modulation waveform here, in this case, I can quickly just by giving a sinusoidal wave, right? So to represent, I'm feeding the control signal to this three-phase converter. So I will just quickly giving the three-phase sinusoidal wave command. So now I would like to give a frequency, like 50 Hertz in this case, and I will give a three-phase voltage output. So in this case, we need to, each of the phase is like 120-degree difference. So I just quickly specify the value here. So now I will also set up our solvers quickly, okay? And then I would like to see how my simulation, dynamics of simulation, if I'm interested in looking at a speed response, so I can quickly just connect to the scope over here. So this is the W represent the speed sensor. And we also have a current sensor over here to allow us to measure in, I'm sorry, this is the angular position. So now we are interested in looking at our speed, so we can quickly just grab to the scope over here. If you are interested in like electrical signal, we can also go to our library again. And in this time, we can go to sensor, and we can quickly grab our current sensor 3-phase, and then can just minimize this block, and then just connect to this line. So then we can, it's a very intuitive, as you know, like in the real world, I mean, in the physical world, especially we are running the experiment, all we know is current sensor is always in series with our circuit, right? So it's very intuitive. You just connect this current sensor in series, and then we can also quickly to see our dynamic response of our current sensor just by connect to this oscilloscope. So now I would like to just set up my simulation time to 3 seconds. So we can quickly see our simulation, how does it, what's the simulation results. So I will just run this button again to simulate our simulation. So as you can see in the simulation is running now, and we can even separate our signal. So as you can see on the top one is our speed feedback showing here, and the lower left is lower corner here is showing our 3-phase current feedback. And now I would like to stop our simulation for a while. And then as you can see, we can zoom in our 3-phase current. One thing to notice is that we are just doing the open loop control here. So as you can see, you can quickly build your own motor control system in the Simulink. And for those of you who are interested in closed loop control, I already built the model beforehand. So just for reference, so as you can see, this is the original physical model. One thing difference is that for doing the closed loop control, you will need the current and position measurement feedback allow you to do closed loop simulation. And in this case, I'm commanding 100 RPM speed command. And also we need some current controller to regulate our current. So now I would like to move back to our presentation. So I have to show you how we can quickly build a motor control system using Simulink. So the next question is, what about control the physical system? How do we control the motor control system? So the good news is with a model-based design, we provide the capability of end-to-end solution from design to implementation. So we can also generate the code directly from your control design to any embedded system. So the workflow here is showing you we have a Simulink simulation, and we can have our controller model and motor model, and we can directly take the controller model for code generation and deploy to the C code, deploy the C code to any embedded software by using embedded coder. So now I would like to show you a video how like that I made to demonstrate the workflow. How do we quickly and easily generate the code with embedded coder? So now we are back to the original model here. So as you can see on the top here, we are clicking the embedded coder icon app, and then we will quickly go to the quick start to generate the code. And it will bring me to a GUI interface to show me the steps that you can follow to allow you to quickly generate the code. So now I will click the next button, and you can choose whether you want to generate a code for entire model or only the subsystem. In this case, we are interested generate a code for the current controller. So we will just choose this one. And as you can see, the current controller, including all the modulation waveform and inverse model. And here you can select what's the output of your generate code. And you will analyze the model to determine how you're going to deploy your generate code. So it's identified now my system have a multi-rate with the 2 periodic rate, and you can choose the hardware processor. In this case, we will just choose the Intel processor. So we can select what's the most important code generation objective. And you can review and give you a recommendation of a configuration parameters change based on your blocks. So now we finished the process for the code generation. And as you can see, the code has been generated. It's a C code of a current.c file. And then the one thing of nice thing about embedded coder is, and now I'm showing you it's around generate about 600 lines of the C code. And one of the nice thing about embedded coder is you can, by clicking the code, it will navigate you to the Simulink block. So it will give you a traceability between your generate code and your Simulink model. So it's really useful for debugging whenever you generate your code from your control algorithm. So we have our generate code from the model, and a lot of times our customer also want to have more confidence on their generate code before they actually deploy to their actual hardware and running the experiment. So running the processor in the loop is one of the approach that can verify your generate code. And this is particularly used in auto and aero defense industry to run processor in the loop to test your controller design. And what it does is in a desktop simulation, you can simulate your control code running on the target and simulate with your motor and inverter model running in the Simulink. And this is helpful for testing the generate code on the target processor. So in addition, for some application, when the computation effort is critical, we can also do some code profiling to identify which portion of your control algorithm take most computation time. And from there, we can optimize your control design. And as an alternative to verify your controller and physical system is using Simulink real-time on target machine. So Spiegel is the Maxwell partnership company focused on designing the hardware real-time controller machine using MATLAB and Simulink. And what makes unique is we can quickly generate the controller code for rapid control prototyping on the dedicated computer that can execute in real time and use the high-speed I/O to communicate with test hardware. And this is a very powerful machine, and with an Intel core processor with many of I/O channels for testing serial communication in real time. And for some people who are interested in running at a higher switching frequency, like megahertz above, Spiegel machine also provide the customized FPGA to generate HDL code if you are interested. So basically in the real-time simulation, there are two approaches they are commonly used in the industry. One is called rapid control prototyping. So basically what it does is you design your controller model in Simulink environment and you can have a planned model in hand. So you can quickly generate a code from your design control algorithm and deploy the code to the target computer. So it is a Spiegel machine. And at the same time, we can refine our control algorithm and tune your PID control on the fly by observing the several signals until we satisfy with our performance of the closed controller system. And the other style of real-time simulation is called hardware in the loop. And this approach becomes super useful when it comes to we don't have a hardware plan model on hand, or our plan model is way too expensive, not allowing us to test in multiple times. So what it means is you can have your target speed go machine will model as a virtual plant model, like for example, in a large scale microgrid power system or the numbers of a generator from the airplane. So you can virtually simulate your physical model into the speed go machine. And as for the controller side, we have our embedded controller hardware like Texas Instrument TIC2000 processor. So we can generate the code from the control model, and we can verify our control design and test the, like doing some fault analyze in our virtual plant model before we actually running the experiment. So today we walk you through the entire model-based design workflow. So from the plant modeling to control design and code generation. So, and we use the toolbox from like Syncscape Electrical to particularly modeling the electrical side for motor control. And for control side, I show you how do we automatically tuning the PI gains to meet our controller design requirement. And I also show you the workflow, how can we quickly generate a code using embedded coder. And all of these toolbox are under the umbrella of MATLAB and Simulink. So basically you can modeling everything in MATLAB and Simulink. And today I just give you guys an example for modeling the motor control system. And of course you can model in other domains as well. And remember, it's a multi-domain simulation system. So it's a lot of capability you can do for your physical model. And now this is an example of our customer using model-based design story. This is an ITK engineer, and they are part of Bosch. They needed to develop a sensorless field orientation control in their new brushless motor for dental drill application. And one of the special things is they start modeling the motor and control algorithm even before motor prototype was available. So basically they ran closed-loop simulation to correct the issue on the controller side and generate more than 5,000 lines of C code by using embedded coder. After they receive the prototype board and motor, they can quickly test the controller and optimize their control performance. So with the model-based design, they are able to save the development time to meet their IEC medical certificate standard and discover the hardware fault early. And this is another example for model-based design using motor control in medical area. It's a ESACOM design. They trying to design a new surgical stapler by model-based design. And the challenging was that typically they need to outsource their prototype development to the third-party developer. And this approach is really slowing down not only the initial prototype, but also the prototype refinement stage. So after they change to use model-based design, they are able to characterize their motor and build the control model on their own. So once the new hardware arrives in the lab, they can since they already have a stable version of the controller running in a Simulink, so they can quickly go to the lab and test it. So ultimately, again, they can save the development time and also unify a different domain of expertise directly in the motor controller. So just want to let you know, we have a lot of technical resource that can help with your project, like myself, I'm the application engineer. So if you're interested to learn more about our product and capability, we can always set up a code and evaluate your project and demonstrate the capability of our product. And so we also have trainings for those of you who want to learn more details. We also have a self-paced training course for Simulink, and from Simulink to deep learning and machine learning, and they are all free. And I'm really highly recommend to start from here. And I think now it's a really good time to learn, especially online, because everyone's stay at home nowadays, obviously. And so what's next? Today I show you the high level of motor control workflow using model-based design. And if you are interested in detailed implementation on how do we design field orientation control on permanent magnet machines using motor control blocks, we will have a more advanced webinar coming up next week to show you the workflow. And you can also visit our power electronics control page to learn more about other capabilities for power electronics control project. And finally, you can also get a free trial of the tools that we went over today. And here are all the resources. And I will share all the links in the presentation later on. So thank you everyone for attending this webinar, and I hope you guys have a great day.
Thank you very much. We just now uploading the poll. If you can answer, it's only 4 short questions. We appreciate it. And I see that for now, there are no questions that I don't see any questions now in the chat. If you have anything, you're more than welcome to upload it now. We'll wait a few more minutes. If you have questions, please do. Thanks everyone for being here. See you next time.
Thank you, everyone.
Thank you.